Welcome friends, Igor is here, and in this video we will talk about a general strategy for solving systems of linear equations. In this lesson we will define a system of linear equations, define what it means to solve a system of linear equations, and devise a strategy for solving systems of linear equations. Let's start with defining a building block of system of linear equations, that is a linear equation. A linear equation in variables x1, x2 through xn is an equation of the given fixed form, where a's and b's are numbers, and in general, throughout this course, I'm going to assume that we deal with complex numbers. Now, in most other sources, most other books or video lectures, you will see real numbers used in the introductory course in linear algebra, but in fact, it makes no difference whatsoever for the development of most topics. When the difference between real numbers and complex numbers is going to be essential, I will make a special note of this. A linear equation has this strict, rigorous form. Each variable appears in equation exactly once, and all we can do is multiply variables by constants, add up the results, and equate the result of this addition to yet another constant. Let's look at some examples. In the first example, this is indeed a linear equation because we have two variables, x and y, that are multiplied by constants. We can think of x as being multiplied by 1, y is multiplied by 2, we add up the results, and we set it equal to another constant 1. Next example. This is also a linear equation, even though it is not written in this standard form, but of course you can take y and z to another side, 3 to the right, and you will have a well-defined linear equation in 3 variables. The next example, this is not a linear equation because we multiply 2 variables to each other. This is not allowed, and therefore this is not a linear equation. In this example, this is also not a linear equation, because even though we multiply each variable by a number and add up the results, we take the square root of x3. This is not allowed, so this is not a linear equation. Finally, take a moment to decide if this is a linear equation. It looks like it's not because we have square root, we have exponents, we have logarithms, but these are simply constants. These are numbers. We have x1 multiplied by a number, we have x2 multiplied by a number, so this is a well-defined linear equation. A solution of a linear equation in n variables is an ordered list of n numbers, s1, s2 through sn, such that the equation is satisfied when we substitute the values of these numbers for the corresponding variable. So we substitute the first number in the list for the first variable, the second number in the list for the second variable, and so on. The set of all possible solutions of an equation is called its solution set. So solution set contains all solutions to the given equation and nothing more. Now, it is important to understand what it means to solve an equation. To solve an equation means to find all possible solutions. In other words, to solve an equation means to find its solution set. Let's look at an example. Let's take a simple linear equations in 2 variables and let's try to solve this equation. Remember, to solve an equation means to find all possible solutions. Of course, it is easy to produce some particular solutions of this equation. For example, x equals 1, y equals 0 is definitely a solution because when we substitute 1 for x and 0 for y, the equation becomes a true equality. Both sides are equal to 1. Another solution is, for example, x equals 3, y equals 1. But that is not enough because we need to find all possible solutions. And we know that this equation has infinitely many solutions. How do we know this equation has infinitely many solutions? Well, geometrically, the set of all solutions to this equation is a straight line in a 2-dimensional plane. And we know that any straight line contains infinitely many points. So here's one way to describe an infinite solution set. I'm going to let y be equal to t, where t is an arbitrary number, what we can call a parameter. Then, if y is equal to t, we can then solve for x and x is going to be equal to 1 plus 2t. So one way to describe an infinite solution set in this case is to set one variable to be equal to an arbitrary parameter and express another variable in terms of this parameter. Now, because t can take on infinitely many values and it can be any complex number, this presentation gives the entire infinite solution set. And in fact, now that we have this general form of the infinite solution set, we can construct a lot of particular solutions simply by assigning any value to t. For example, if we let t be equal to 0, we recover the solution x equals 1, y equals 0. If we let t be equal to 1, we recover the solution x equals 3, y equals 1. And you can continue in this fashion. You can construct as many solutions as you like. Now we are ready to formally define what a system of linear equations is. A system of linear equations, or simply a linear system, is a finite collection of linear equations. I'm going to specifically emphasize definition of the terms in this course because learning mathematics is like learning a foreign language, and definitions of terms is your vocabulary. If you don't know what exactly a mathematical term means, you cannot possibly use this term because you don't understand what this term entails. Linear system looks like. Let's say we have a system of m equations in n variables, x1 through xn. Then such a system has the following general form where a's are complex numbers and b's are also numbers. So notice that in this system, each equation is a linear equation. Now, it is not immediately clear from the definition that any linear system can be written in this strict rectangular form, because that general form says that all equations in the system involve the same collection of variables. Yet the definition doesn't say that all equations in the system have to involve the same variables. Let me convince you that every linear system in fact can be written in this rectangular general form. Let's take a pretty bad case. I'm going to take two linear equation. The first equation is going to be in two variables, u and v, and the second equation is going to be in three variables, x, y, and z. Now, these equations share no variables at all, yet I claim they comprise a well-defined linear system. Let's write these equations next to each other, and let's make sure that we kind of separate vertically the variables into separate columns. You see the idea now? I can assume that the first equation also includes variables x, y, and z, but they are multiplied by zeros, so they are not explicitly present in the equation. And the second equation includes variables u and v, which are also multiplied by zeros, and they are not explicitly present in the equation. Additionally, if you like to label the variables as x1, x2, and so on, we can make a simple change of variables and we can represent our system of two equations in 5 variables, and these variables can be labeled as x1, x2 through x5. Now that we understand what a linear system is, let's define what it means to solve a linear system. An ordered list of numbers s1, s2 through sn is a solution of linear system in n variables if it is a solution of every equation in this system. To solve a linear system means to find all the possible solutions of the system, that is, to find the solution set of the linear system. In particular, because solutions of a linear system must be solutions of every equation in the linear system, the solution set of a linear system is the intersection of solution sets of every single linear equation that comprises the system. Let's look at some simple examples. In the first example, we have a linear system of two equations in two variables. Then x equals 1, y equals 1 is a solution of this system because it satisfies the first equation and it also satisfies the second equation. But x equals 2, y equals 2 is not a solution of this system because it satisfies the first equation but not the second one. Here's another example. We have a linear system with two variables and two equations. Can you name at least one solution of this system? No, you can't, because this system has no solutions. Do you see why? If you have values of x and y that satisfy the first equation, then 2x plus 2y will have to be equal to 4. It will never be equal to 8. And therefore, these two equations share no common solutions. And in this case, we say that the system has no solutions and its solution set is empty. From these simple examples, we see that a linear system might have some solutions as well as it might have no solutions. So it's natural to ask, what are the possibilities on the number of solutions of a typical linear system? We can quickly answer this question in a special case of a linear system in two equations and two variables. We know that a linear equation in two variables defines a straight line in a two-dimensional plane. A solution to a linear system is a solution to both equations, therefore geometrically, a solution to such a linear system is a point that lies on both lines. But there are only three possible ways how two straight lines can be arranged on a plane. The two lines can be parallel, in which case they have no points in common, and in this case this system has no solutions. The two lines can intersect, and straight lines can intersect only at a single point. In this case, the system has a unique solution, exactly one solution, or two lines can in fact coincide. They can be the same line. In this case, they share infinitely many points, and such a linear system has infinitely many solutions. This argument proves that a linear system in two equations in two variables has only three possible solution sets. Empty solution set, no solutions, a solution set with exactly one solution, unique solution, or an infinite solution set which contains infinitely many solutions. In fact, this is true in general for any linear system. Any linear system has either no solutions, exactly one solution, or infinitely many solutions, and we will be able to prove this fact fairly soon. Given a linear system, our most immediate goal is to find its solution set. For this reason, if different linear systems have identical solution sets, we will think of these systems as equivalent systems. And this is a definition of equivalent systems. Two linear systems are equivalent if they have the same solution set. Here's an example. We have two linear systems, and both of these linear systems have the same solution set. It consists of a single unique equation, x equals 1, y equals 0. So we will call these two linear systems equivalent, even though they may look different, but in the end, they reduce to the same solution set. And this remark gives us a great idea for a general strategy how to solve linear systems. We start with some possibly complicated linear system, and we're looking for its solution set. So the idea is to replace the original system with an equivalent system that is easy to solve. And because the new system is equivalent to the original one, they will have identical solution sets. So here is a strategy. Start with an original system which is possibly difficult to solve. Transform this system into an equivalent system which is easy to solve. Find the solution set for the transformed system, and that solution set is the solution set of the original system you're looking for. To implement this strategy, we need to be able to do two things. First of all, we need to know what we can do to a system so that the transformed system is equivalent to the original one, which kinds of transformations preserve the solution sets, and secondly, we need to know what to look for. What kinds of systems are easy to solve? If you found this video helpful, please like and subscribe to help others discover this content. In the next video in this series, we will discover what transformations preserve solution sets of linear systems. I will see you later.